Hey, how's it going, Stefan? I decided that the quickest way to get my first idea to you would be to just do a quick private video. Essentially what we're looking at here is a pressure vessel that I will be building from a small argon bottle, a 5,000 psi bottle, a very thick steel bottle. And the way we will control the temperature of that bottle is with a internal stainless steel coil, which I will spin to a specific shape to fit inside this bottle, and it will have either hot or cold fluid circulated through it. This little box here will have a valve system in there with a pump that will pump either hot water or cold water through this internal coil, depending on what cycle we are injecting into the system here, or attempting to induce, I guess I should say. So we would have a thermocouple connected to the vessel. The exterior of the vessel, it wouldn't necessarily need to be insulated because the outer walls will have heating coils and cooling coils. And there will also be another coil just like this on the inside area here as well, so that there isn't that big of a fluid gap in between the heating element and the fluid itself. This would allow us to observe the effects on a piston. Now, this piston will actually be way smaller than this, and we might even use a pressure booster strategy that I deployed some years ago when I was doing testing with this. I'm going to send you guys some video links to some acetone testing that I've done to show you what I came up with, because I don't think you guys have seen all the videos. But the reason why I want to put this coil on the inside is because it can handle the high pressures that will be induced. Now, this right here is a valve. We will simply be cracking the valve when we want to release the pressure onto the piston. Using a block to block the movement of the piston or lock it in place would be extremely difficult to work with in practice. The high pressure induced from the expanding acetone would make it very hard to remove any key or cotter that we may have inserted to obstruct the movement of the piston. It would cause a lot of damage when it was released, scraping and marring. And I know from experience that you can just crack a valve very easily to release this pressure and even control the flow rate. You can open it very quickly and get an explosive release, which is what I would recommend in practice when we were using this to run an engine. The pressure would be built up inside the bottle, a high-speed valve would be released, and then the pressure would be explosively inserted into the piston. And I have some extensive diagrams on machines. I'll attempt to find some of that for you real quick. Okay, Stefan, I've been sitting on a lot of these diagrams and stuff for years and years, and I'm willing to give it all to you guys to help you with your project. This right here is a fluid distributor for a more advanced liquid metal motor. I was going to use liquid mercury as the expansion medium and a kinetic motor. Acetone can also be used, and the idea was that mercury would be confined in a space and expanded, and these cam distributors here would explosively release the confined pressure into a hydrostatic drive motor. Now, this is a very crude drawing of that motor, but this is kind of what it looks like. And I did start to finish the motor. Here's a more complex view of the motor itself. You can see the kinetic actuators. These are what the pistons actually look like. And there's a radial array of those pistons. And each one is connected to a large array of acetone tanks that are heated and cooled. And this motor might be connected to 300 tanks or something crazy, so that every half a second an explosive release of force is allowed into this motor. I have more drawings of this motor somewhere. I just haven't had time to gather them all for you. I've got some other stuff here. Oops. Here is another version of that same motor. And as you can see, I have done some extensive work. This right here is called a kinetic converter. And basically, it's kind of like the idea I just showed you guys. It's a special high pressure bottle that has some coolant and heating loops inside of it. And these coolant and heating loops allow rapid expansion and contraction of the fluid inside of there. And what we would do is have a huge array of these things. Let me see what we got here. Here's a kinetic actuator, one of the pistons. I've done all the math on this stuff years ago too. A lot of math. Here's another look at the kinetic converter. And this is kind of what the thing looks like. I have a picture of the way these would be set. Oh, this is something different here. That's the ratchet mechanism for one of the motors. I was trying to show you what this thing looks like. Is this it? Here we go. This is a kinetic actuator array where we have hundreds of these things connected all over, and they supply the pressure to that. Here's a top and side view of these. And these are the actuators that use the hot and cold junction to power these various motors. This particular motor is another way of pulling that off. This is a very small piston exposed to a very high pressure region, but it's a very low expansion rate. So because of that very low expansion rate, we can use a very small piston. And you can see here, I've got a lot of information to share with you guys. A lot of diagrams to print out and send to you. We have a lot to look at. You know, this may be a waste of your guys' time right here, all these diagrams and stuff, but there's another form of that kinetic engine. I've got several ways of using this high pressure to actuate an engine. This is the ratchet engine, and that uses a special ratchet mechanism. Here are some details regarding how we would connect all this stuff. The timing sequence of the engine and all that. So my favorite one was the hydrostatic version of this. Man, I wish I could find the actual, what's this here? Let's try. I've got hundreds of files to share with you. Oh yeah, here we go. Well, maybe not. This is an old version. This is where I was just starting to put that engine together. I start off with a rough draft like this, and then I turn it into, oh, here it is. This is it, you guys. This is the motor. So you see here, when these little actuators are pressed by a cam, this fluid gate is connected right here and allows that high pressure fluid from this fluid distributor to press on these hydrostatic pistons. And they press on this lobe, this eccentric lobe, the swash plate, and that's what causes the rotation. This is a side view of a hydrostatic motor that uses the extreme high pressure, low volume expansion of a fluid and turns it into rotary motion. But it's releasing an explosive motion. We're not slowly cracking a valve here. And this whole assembly rotates, and these pins right here would rub up against the cam that would push them in and out to either open or close the fluid to this piston. And that would cause a very high-speed rotation. So this is some of the beginning work that I have done on this project, and I want to show you guys another thing here. I'm going to share with you guys my lab work on some stuff that I've done here, okay? This little machine right here is a pressure booster that I built, okay? And what it does is it takes the high pressure from the expanding side here and boosts the pressure. This is a very low volumetric expansion, which I did all the calculations on here. And what that does is it presses this rod, which is connected to a bigger piston, which moves a larger volume of fluid. And you can see here I have a check valve assembly that I was working with. And this enables us to take that very small, high pressure movement and turn it into a larger, more usable flow. So we could go from, say, 50,000 psi's at 1 liter per minute to 3,000 psi's at 200 liters per minute, which is a usable turbine or fluid motor flow. So that is the purpose of this fluid booster. It's kind of like the opposite of a pressure booster. It converts high pressure, low flow into low pressure, high flow so that we can run a motor on it without breaking things. All of this is testing that I've done. I put acetone inside a confined container and did a bunch of research on the effects. So I'm definitely willing to share all of this information with you guys. I'll kind of scan over it so you can see what I was doing. A lot of it resembles your work indefinitely. You can see here we've got the little spring and the piston you guys were talking about. So I've already done a lot of this stuff. And I have a lot to share with you. Here's my heating coils that I was telling you about. This is the way to do it, you guys. Right here. We heat the fluid up inside of the container. When the pressure gets where we want it, we open this valve to release the fluid into the piston. And these are various equations that I am very fluent in. This is the apparent volumetric coefficient of thermal expansion. This is a very useful equation right here. This is going to come in handy for us. It's either the realistic or the apparent. I can't remember, but the apparent change in volume is what this, or the realistic change in volume. Excuse me. Here's some other data for you guys. We wanted to share this all with you. You can pause this video and get a quick look. Here's a 1 liter of acetone, okay? I already did a lot of the research on this and came up with change in pressure of 10,000 psi. Well, I wrote wrong on here. I must have found something out and redid this. For some reason, I wrote wrong on that. But nonetheless, you can see I've done a lot of the equations already on 1 liter. Get you guys a little scan of that. Here is a little bit more work that I had going on. This is a device that I actually built, a confined space fluid device. It looked like this in cross section. And I believe this is some of the data from the kinetic actuator that I built, and I have videos on all this stuff as well. This is a graph that I drew up based on an acetone coil that I built. There was acetone trapped inside a copper coil, and I set that coil inside a hot tub of water and a cold tub of water right next to each other. And this is some of the data that I got out of that. And this is a graph that I drew. It kind of shows a correlation in events. And oddly enough, the heat up cycle is slower than the cool off cycle. So the pressure rise when you put it in hot water is slower than when you put it in cold water. When you put a hot coil in cold water, there's a drastic, sharp drop in pressure. Very neat situation there. That pretty much is about all of it, guys. That is some of my beginning work. And like I said, I've got a lot of videos on these experiments that I can share with you guys. This device here is something we may want to replicate to make your experiments more observable. 1 liter, I think, gives you about this much expansion, if I'm correct. I'll have to double check this. 5.49 milliliters from 1 liter of acetone expansion, I think. I'll have to double check this. This might be an oil test, actually. Don't quote me on that. This may be oil. But another thing I like to do is separate the acetone from the seals in the piston by putting a oil slug in between the two fluids. So, all right, I'm babbling at this point, guys. I think that kind of gives you the gist of it. The device that I want to build for you is definitely going to be this guy right here. Pretty good way of looking at it. And I've also done some horsepower equations on the flow. So I've done quite a bit of math on this, guys. This is just some of it.